Students, in this lecture we discuss with cells in series and parallel as resistance and capacitor also arranged in series and parallel. Similarly, cells also can be grouped in two ways. One is series and another is parallel. So, first cells in series. Two or more cells are said to be in series if they are connected one after the other. The definition is same as we use in resistance and in case of capacitor. Okay, once again, two or more cells are said to be in series if they are connected one after the other. Okay, now here two cells, one is of EMF E1 and another is of EMF E2 with internal resistance R1 and R2 are connected between point A and B and another between point B and C. Okay, through which current I is flowing. Okay, so potential difference between A and B, potential difference, and this is terminal potential difference. Okay, so VAB, the potential difference between A and B is equal to VA minus VB, and that is equal to E1 minus IR1, because we know the formula V is equal to E minus IR. The relation between terminal potential difference and EMF of cell. This is equation 1. Okay. Similarly, potential difference between B and C, that is VBC is equal to VB minus VC is equal to E2 minus IR2. This is equation 2. Now, potential difference between A and C. Potential difference between A and C, that is VAC is equal to VA minus VC. Okay. Now, if we subtract minus VB and add VB in this equation, then there is no effect. So we get VAC is equal to VA minus VB plus VB minus VC. But VA minus VB is equal to VAB and VB minus VC is equal to VBC. Okay, so VAC is equal to VAB plus VBC. Okay, put the value of VAB from equation 1 and from equation 2. We get VAC is equal to E1 minus IR1 plus E2 minus IR2. Okay, then separate EMF and internal resistance, then we get E1 plus E2 minus, because I is common, so minus I R1 plus R2. Equation number 3. Okay, now if we replace this combination, by a cell of EMF E and internal resistance R, through which a current I, the same current, through which current I is flowing, then VAC is equal to E minus IR, because the cell of EMF E and internal resistance R is connected between point A and C, through which current I is flowing. Okay, comparing equation 3 and 4, we get total EMF E is equal to E1 plus E2. This is in case of two cells. If there are three cells, then plus E3, and if there are n cells, then plus E3 and up to En. Okay. Similarly, the internal resistance R is equal to R1 plus R. Okay. Here, when two cells are connected in series, then EMF increases, but with the increase in EMF, internal resistance also increases. Okay. Now, the cells in parallel. Two or more cells are said to be in parallel if one terminal of all cells are connected to one common point. B1. Okay. For example, and another terminal of all cells are connected to another common point, for example B2. Okay. Now, from figure, total current in circuit is I1 plus I2, that is equal to I. So, I is equal to I1 plus I2. But we know the formula, V is equal to E minus IR. Then I is equal to E minus V upon R. By this formula, we get I is equal to E minus V upon R. So, for I1, E1 minus V upon R1, and for I2, E2 minus V upon R2. In case of parallel, the potential difference remain same because both the cells are connected to same common points. Okay. Then I is equal to E1 upon R1 minus V upon R1 plus E2 upon R2 minus V upon R2. In next step, E1 upon R1 plus E2 upon R2, and because V is common, so minus V 1 upon R1 plus 1 upon R2. This is equation 1. Okay. Now, if the combination is replaced by a cell of EMF E and internal resistance R. EMF E and internal resistance R, through which current I is flowing. Then V is equal to E minus IR, the relationship between terminal potential difference and EMF. By this formula, we get I is equal to E minus V upon R or E upon R minus V upon R. Equation number 2. Comparing equation 1 and 2, we get E upon R is equal to E1 upon R1 plus E2 upon R2, or E upon R, by taking the LCM, we get E1 R2 plus E2 R1 upon R1 R2. And internal resistance 1 upon R is equal to 1 upon R1 plus 1 upon R2. By taking LCM, we get 1 upon R is equal to R1 plus R2 upon R1 R2. Then, from equation 3 and 4, because 1 upon R is also in equation number 3, then we get E is equal to E1 R2 plus E2 R1 upon R1 plus R2. This is the resultant EMF and this is resultant internal resistance. In case of parallel combination, internal resistance decreases. When you calculate by this formula, this is similar to resistances in parallel, and as you know that the resistances in parallel decreases. Okay, in series resistance increases and in parallel resistance decreases. So in when two or more cells are connected in parallel, then internal resistance of cells decreases. Okay, some extent EMF decreases, but this can be negotiated. Okay, now a new topic, Kirchhoff rules or laws. Okay, two rules called Kirchhoff rules which are very useful for analyzing electric circuits. Kirchhoff rules, one important topic for board examination. So Kirchhoff rules are the two rules which are very useful for analyzing electric circuits. These two rules are, one is junction rule and another is loop rule. They will discuss in next lecture. Okay.